Okay, so let's go to our lecture contents. Um, so previously we have introduced Poisson equation. So of course Poisson equation can have a more general form, but when I write down in this way, so it is already considering certain form of electron density and hole density. So here we have an expression for electron density and hole density in terms of a function of a potential. But unfortunately, usually I prefer to have this kind of notation. So electron density is really dependent on the electrostatic potential, but here we have a leading coefficient corresponding to the intrinsic carrier density. This is the more general expression for electrostatic potential, but in this case we have intentionally introduced a little bit different, actually offset one. So phi here, so we have a different coefficient here. Previously we had the balanced one, intrinsic carrier density, but now this is for N MOSFET, this is extremely small. On the other hand, this one is extremely large. So please understand this one. So anyway, now we have this Poisson equation, and previously I told you that actually this equation is quite accurate without approximation. So I have to modify my statement. Instead of exact number, so there is an approximation like P equal to infinity is approximated as acceptor doping, but I think that this is really acceptable. So for example, if you apply 10 to the 17 per cubic centimeter as your Na, then your hole density is also corresponding to that number, 10 to the 17, with small, really small error. So I think that it is completely okay to write down in this way. But if you are concerned, then please write down instead of this Na, you may say piece of infinity. Well, now this is Poisson equation, and at the end of our previous lecture I told you that we have to multiply something and integrate this equation. But natural question is why we have to do that. Here we have a Poisson equation. Yes, now Poisson equation is given, but now I'm saying that multiplying something corresponding to certain weighting factor, position dependent weighting factor, after that integrated over entire simulation domain or our MOS domain. So not entire, starting from 0 up to infinity. So this is corresponding to, of course, this domain is corresponding to the silicon part or semiconductor part. That was my final comment on our general procedure to derive something. Natural question is why we have to do this kind of job. Here we have an equation. Then what happens if we just integrate this Poisson equation without any weighting factor? So it means that if we just multiply number 1, so nothing happens. Then if we integrate it over our domain, then what will happen? First of all, let's think about this one. Okay. So here we have a Poisson equation, and when we make an integration without multiplying anything, so then what we will get is integration and integration over certain domain starting from 0 to infinity and 0 to infinity, and of course we must infinitesimal length to make this integration valid. So if we have do this job, then what we will have is quite clear. We will have d phi over dx evaluated at infinitely deep position minus d phi over dx evaluated at the surface position. And please try to simplify it. Here we have two terms, d phi over dx evaluated at x equal to infinity and 0. Of course, this quantity is not that easy to evaluate it. So actually this is our goal, to find out the electric field at surface. But we can make a further simplification here. This is d phi over dx. What is it? This is the electric field, actually minus electric field at deep substrate. At deep substrate, we have already considering the neutral condition and no electric field exists. So we can safely say this is gone. So we will just have d phi over d minus d phi over dx evaluated at x equal to 0, and this is nothing but the electric field evaluated at x equal to 0. Yes. And the next one, in order to evaluate this equation, so here we have integration variable of x, and the integrand contains here and there the function phi of x. So if we have no idea about the specific form of electrostatic potential, actually we cannot integrate it. So its integration is not that easy, but what we can say is quite simple. Since we have made integration, this is nothing but 0 to infinity and minus rho epsilon and its integration. That's it. So simply speaking, when we integrate this charge in entire substrate, then we will have actually Q itself. That will be Q. Integration of our space charge over entire surface will give us just number Q, and here we have a minus epsilon. That's it. So when we make the integration of our pure Poisson equation, the result is amazingly simple. Amazingly simple means that electric field at x equal 0 is simply given as Qs semiconductor charge divided by epsilon silicon. Of course we have a minus sign. This is nothing but just integration of our Poisson equation. So let me just repeat this job once again. Here we have the original form of our Poisson equation. You know, this is corresponding to the Coulomb's law. And what we have done up to now is just a simple one-dimensional expression of this operation. So we wanted to integrate our Poisson equation over real space. So let me just do it. So integrate this Poisson equation over our real space. Since this is in general three-dimensional space, I will just write down in this way. And of course, integration domain is required, and let's call it as omega. So how does the omega look like? So it depends. So depending on your problem, you can define in this way. So this is the left-hand side term. Then please repeat with your right-hand side term. How can you do that? This is really easy to write down in this way. So by doing this job, then you can clearly identify this left-hand side term is nothing but just to integrate charge all over your simulation domain omega. So this is corresponding to the net charge. So you know this, usually this law is volume charge, so you will have coulomb per cubic centimeter, and you make this volume integration, so this per cubic centimeter term is gone, and you will have just net charge without any normalization, so you will have a coulomb. Yes, so this is not that difficult to follow. However, please have a look at this left hand side term once again. When you have a look at this one, we have a general form of this way: integration, volume integration of certain divergence. So maybe you have heard about this form. When you have a volume integration of a divergence of a vector field, then it can be converted into what? Just a surface integration of normal component. So that now it can be just converted into this way, and of course in this case the integration should be done over surface of our integration domain omega. Sometimes people write down in this way, but well, I'm not quite sure we can understand this one. So now anyway, we have to do the surface integration of this quantity. Why I'm talking about this general form? So now we have this form. Yes, D, and it's dA, and surface of omega equal to the net charge inside our entire system. Then now think about the shape of omega in our case. How omega looks like? Can you imagine? Our omega in this sense, this should be up volume. Then let me just write down in this way. Here we have x-axis, and this point is corresponding to x equal to 0. And where do we have our substrate contact? Substrate contact is located this x equal to infinity position. Then since we are talking about three-dimensional coordinate system, then now we have just one real space axis, x. How about y and z? In this case, we just assume that this is homogeneous. So for y, and if we have just right-handed rule, then we will have this z. So are you with me? In this case, if I just make a tilted view of this equation or this system, then I will write down in that way. Yes, we have a very wide box. This box, and we have x-axis and y-axis, and actually this is corresponding to our z-axis. Along y, along z, how large is it? It doesn't matter, because we will just consider homogeneous system along y direction and z direction. Only important quantity is the area. It is area A. So, wow. Now let's think about this one. When we say I wanted to integrate just number 1 over our system called as omega, it can be converted into this way. So it is corresponding to dx, dy, dz, for example. Then this is corresponding to from 0 to infinity for x, and y 0 to L y, and for z 0 to L z. So our area is corresponding to the product between Lx and Ly. So are you with me? Therefore, if this integrand is just a function of x instead of a function of y and z, then this integration over dy dz can be just safely converted into just multiplication of area. So now we can write down in this way. It can be just multiplying area and integration over our quantity over dx. So are you all with me? So I have told you some points. One is, although I just show you the integration of Poisson equation in our 1D system, it was not that difficult. But we can also discuss in more generalized way using vector notation. But still, it is quite easy. Now we have to consider the volume integration over omega. However, when volume is specifically easy, like a box, our box, then we can write down this triple integration, and dy integration, dz integration can be just converted into a multiplication factor of area, and the remaining thing is only this one, the only one, yes, integration over x. Why we are bothered with this kind of dimension conversion? Because later, right now we are just considering MOS capacitor. Everything is homogeneous. However, soon after, we will move into non-homogeneous system position-wise. So that is called as what? Called as MOSFET. If we consider MOSFET, the physical quantity, such as electrostatic potential, is no longer homogeneous along y direction. So we have to consider position-dependent one. So that's the reason why we are currently talking about the general expression for this one. Okay, so now let's come back to this one. Then now, please try to express this surface of omega integration for this quantity. Then you can identify 6 different faces. Yes, so let's call it, this box has omega. Then you can identify 6 different faces, but 4 of them are actually meaningless. Why they are meaningless? Because this is corresponding to that direction, and another one is heading this direction, and another one, and another one. Their normal components are just aligned y direction or z direction. But you know, this d vector, displacement vector, can be, in our case, safely heading only x direction. There is no y direction and no z directional component of our displacement. So in this case, 4 different faces are just meaningless, and only 2 meaningful ones are the one at heading this way and the one heading at this way. Of course, this upper or lower surface is corresponding to x equal to infinity, and x equal to infinity also displacement is gone, so we don't have to care about this fifth one, and the only remaining one is the first one or the last one shown here. This is corresponding to x equal to 0 coordinate, and in this case, let me just write down this dA. Our dA can be safely written down in this way. Area times minus x. Are you with me? The direction is minus x, and area is just area of our system, Ly times Lg. So this is the result. So what we can say is, although we have quite a complicated behavior or equation at first glance, but it can be written down in this way. X equal to 0 multiplied by, minus area. That's it for our integration, surface integration. We had 6 faces, but 5 of them are meaningless. Only the one at x equal to 0 makes some meaningful result, and area is just area, and the sign is minus x-axis. So now we can write down this way. So please understand this kind of a simplification. We will later use this kind of operation many times. But let's just come back to our main discussion. Well, today's lecture starts from this simple question. Our procedure is to multiply this weighting factor. Yes, we can do it. If 1 equal to 1, then if we multiply something 3 to right hand side and left hand side, then still we will have equality. That is our procedure. The weighting factor, any arbitrary weighting factor can be multiplied to the system, and the equality should hold every at every weighting factor. So that was our argument, but we tested weighting factor equal to 1, and the result is, what was the result? The result is so trivial. The amount of charge inside the semiconductor part is corresponding to the surface electric field. Nothing but just if we have a non-zero net charge, then that will affect our surface potential. On the other hand, if we have a net neutrality inside the semiconductor, then surface field will vanish. It's quite simple. So we have a one-to-one correspondence between our surface electric field and entire amount of charges in the semiconductor region. So that is so trivial. One, well, so please note that the main driving force to evaluate this one is this kind of tedious calculation is we wanted to find out the relation between surface field and surface potential, but the result we have obtained with just simply integrating Poisson equation is surface field and net charge. So if we can find something, so how if we can express Qs in terms of phi s by some means, then we will be very happy, but it's not that easy. So that's the reason why, well, what we wanted to do is eventually find out this relation. So we have to try different weighting factor. Okay. So I think that can my discussion can give you sufficient motivation for why we have to introduce different weighting factor. Then quite a natural question is, then why this specific choice of weighting factor is required for our discussion? Maybe we can try different weighting factors. Yes, you may. But point is, if you try another form, then maybe the resultant equations are so lengthy and it contains other so many different terms. So it is not useful in its practical sense. That's the reason why we use quite a simple, seemingly arbitrary value. So this one. Okay. So do you have any question up to now? So what I try to deliver you up to now is we need some motivation about this kind of weighting factor. Okay. So let me just do it from now on. Yes, please.
웨이팅 팩터가 그 아까 그 전체 전화수랑 그 표면의 전기장이 1대1 비율이 좀 나오셨는데 근데 그 전기장을 그러면 그 그러니까 전화 텀이 있는데 그 전화 텀을 전위로 바꾸기 위해서 웨이팅 팩터가
No. So, okay. So, her question was, so by integrating the Poisson equation quite a simple way, we can find the relation between ES and QS. However, our goal is to find out this one. If we can find the relation between QS and phi S, then by combining these two, we will find this form. However, actually finding this form is not that easy. So this pathway is not available. So instead of that, we just directly try to find out this expression. And it can be done by just multiplying this weighting factor and integrating the Poisson equation all over our simulation domain. So we will not follow this way. We can find this expression, and from this one actually we can also try to find out this expression, because ES and QS can be regarded as almost the same quantity with just a simple proportional coefficient. Here ES and QS, they have quite a simple proportional coefficient, so you can just directly compare to one to the other. Okay, that is a good question. And as I told you repeatedly, the beauty of this planar system is by doing this job for planar system, we can find out clear relationship between surface potential and surface electric field. Unfortunately, for different systems like general double gate MOSFET or other kind of MOS system, analytic expression is not available. So that's a pity, but well, anyhow we have to live with this situation. Okay, so anyway, this is really important. Okay, so let me just do it together with you. Here now we have d phi over dx, and previously we have a second derivative of d, and now we have dx. Please note that that was the left hand side of our Poisson equation originally, and we have multiplied just a simple weighting factor, and we wanted to manipulate it. Okay, so are you with me? So let me just do it this way, here and there, minus minus, nothing happens because minus minus gives you just a positive, number one. Yes, and let's identify E as this one. This is really corresponding to the original definition of electric field. E is corresponding to the electric field, and electric field is given as gradient of electrostatic potential, and it's a minus term. Now, if we introduce this kind of a variable change, so you can easily identify this is E, and the second term is corresponding to dE over dx. Are you with me? So dx. And the next one is, here we have E and dE over dx, and it can be written as half and dx and E square. It is really easy to the equivalence between this expression and that expression. You can just do it. Then you will find that E times dE over dx is really obtained from evaluating this job. Okay. So simply speaking, the left-hand side of our Poisson equation multiplied by this weighting factor becomes just square of electric field, its derivative and integration. So let me just do the integration. Then how can I do that? So starting from 0 to infinity, I would like to integrate the first derivative of a squared electric field, and it will give us half times squared electric field evaluated at infinity position minus half of electric field squared evaluated at 0 position. Once again, since electric field itself vanishes at x equal to infinity at deep substrate, the first term does not contribute anything. And the second part is also quite easy to understand, because we have assumed the homogeneity of our electric field with respect to y and with respect to z. So it can be simply written as, although this is squared electric field, but it can be write down just electric field at x equal to 0 and it's square. Sometimes it may different. I mean that average of electric field and its square, and square average of squared electric field, they can be different in general situation. If we have inhomogeneity along y direction and z direction, then maybe they can show some differences. But fortunately, in this MOS capacitor, we assume that everything is just a function of position x, and position x is the same. So we can simply write down in this way. Okay. So up to now, I have just done the left-hand side of our Poisson equation, but now let's go to the right-hand side of our Poisson equation. Previously, we wanted to integrate it this way, but unfortunately, this one has the function of phi. Oh, so we were not able analytically integrate this right-hand side term. But fortunately, by multiplying this weighting factor, now we just multiply d phi term. So the right-hand side term now can be simply written as this one. All of our integrand are just a mere function of surface potential, and now we perform the integration over that potential. Oh, sorry, I made the surface potential, but sorry about that. This is not surface potential, but potential, electrostatic potential, and we have to do the integration over that potential. So this integration can be done without much difficulty. Why? Let's have a look at those terms. the first term is just exponential of phi. If we have exponential minus phi, and if we have to integrate it over this one, then we will have just minus and the same form. And also here you can see that the one with positive sign, and this positive sign give us just a positive sign. So the first term and the third term can be easily integrated. And how about the second term? Oh, this is nothing but just minus NA. Oh, this one gives us just a phi. And here we have also similar term, just constants. So we will have just phi dependent term. So this integration can be done quite easily. So now you find this form. Oh, left hand side term becomes just integration. Oh, sorry. So square of electric field, and the right hand side term gives us certain numbers. Oh, but we had previously 4 terms, and now we are saying that there are many other terms. 1, 2, 3, 4, 5, 6. Why do we have this kind of numbers? Please try to do it by yourself. You can do it. And after that, now we can find certain form. Here, please note that in this case, integration starts from 0 and ends at not infinity, but any arbitrary value of x. So that's the reason why here we have x, but let's just do this job. So by specifying certain concrete lower limit and upper limit, and eventually we can find this one. Yes, so surface electric field, sorry about that, not exactly surface electric field, but it is important, square of surface electric field. Just integrating Poisson equation gave you surface electric field, but that doesn't give you any further information. But by multiplying a clever weighting factor, now you get square of surface electric field, and it is given as this seemingly quite a complicated form. But from this one, what you can do is, okay, ES is given as entire square root of this right hand side term. Are you with me? But you may ask me one further question. This is a square. For example, let's say that x square equal to 4. Then x equal to 2. Is it right? Or no? So we have to consider also pairs of these two square root, so plus minus. So obviously we can find plus and minus. However, please think about this way. If we have gate voltage higher than flat band voltage, then what happens? Now we have a higher potential and lower potential in this metal part. Here we have a higher potential and relatively low potential in substrate. Here sub and metal. So direction of electric field is always from high potential to the low potential. We have a positive electric field. So in this case, we can write down electric field becomes positive. So although in its calculation, we can find two different candidates for ES, but using the physical consideration, we have to select this positive one. On the other hand, if we have gate voltage lower than, even lower than flat band voltage, then how does it look like? now we have sufficiently low potential in metal part and relatively high potential in the substrate, and the direction of our electric field now heading negative way. So in this case we have to multiply or select minus sign for our calculation. Okay, so that is the one. But in many cases we just consider the bias voltage higher than flat band voltage because we wanted to use this MOS system as a part of enhancement mode MOSFET. So usually we consider this bias condition higher than flat band case. Okay, so now we know surface potential, and surface potential can be easily converted into integrated charge inside the semiconductor region by multiplying something. So now you will have this form. Okay, once again here we have a positive negative sign, but please note that if we have gate equal gate voltage higher than flat band voltage, then we have to select this negative sign. So please think about this one. Now we have this oxide region, and here we have a metal and semiconductor, and now I am assuming that gate voltage is sufficiently high, and I'm saying that the charge collected in the semiconductor region is negatively charged. So is it true, and is it consistent to your understanding? So this is a relatively high potential, high voltage biased, and this is a relatively low voltage biased. So what you can expect is there is a collected positive charges, and there should be collected negative charges. So if we consider the charge found in the semiconductor region, so in this part, they should be negative, and it is consistent to our understanding. Okay, so although we have applied positive bias, but what we are currently talking about is not this metal charge. Of course, at the metal side, we have the exact amount of charge collected in this metal plate, and they are positively charged. And here we have a negatively charged charge sheet. So please let me know if you don't understand my explanation. And now here we have several terms. Six different terms. Of course, here we have a leading factor, but it is just given. And depending on our surface potential, the importance of these terms, relative importance of these terms, are changing. So let me just discuss. First of all, you have to understand there are huge difference between overall coefficient. So here we have a big parenthesis and another big parenthesis, and please try to estimate the leading coefficient for each of these two big parentheses. What is the coefficient? Here we have just a unity, number 1, and here we have ni squared divided by na squared. Oh, ni squared, its value at 300 Kelvin is given as per cubic centimeter unit 10 to the 20 per minus 6 power of a centimeter, because this is just squared. And please have your Na value in your mind, 17, 18, then please try to make a square of it. Then you will have 10 to the 34 or 10 to the 36. And when you just do this math, then what you will get is a uniqueness number corresponding to 10 to the minus 14 or 10 to the minus 16. Wow. So when you have a look at these two terms, although they are just looks balanced, but they are not balanced. The second parenthesis has a really huge penalty factor, like 10 to the minus 14 or 10 to the minus 16. So the only way to this second term overcome the first term is, which one is the possible candidate for overcoming this huge penalty factor? So only this guy can possibly contribute to its magnitude. You know, this is just a linear function of our surface potential, and surface potential at most its value can be at most just 1 volt or slightly higher. This is the maximum for our surface potential. And when it is divided by summer voltage, then its maximum number is about 40. Here we have 10 to the minus 14 or 10 to the minus 16 and multiply 40. Then what will happen? That doesn't contribute at all. So it never contributes to overcoming this first term. However, please think about this one. Here we have another one, exponential. If we have, for example, here 40 exponential, that can make a certain. So, for example, if we have 1 volt of bending, so this can really overcome the values orders of, for example, 16 decays difference or 17 decays difference can be overcome by this 1 volt surface potential. So that's the key. Here, these terms start from great penalty. However, among 3 of them, this guy have a certain potential or some possibility to overcome huge penalty factor. So this term is quite important. That's the reason why I highlighted this term. Okay, this is quite a special case, and let's consider more usual case. Well, the case where this term contribute quite a lot is phi s is almost close to 1 volt. Otherwise, then this term doesn't contribute at all. Then we have to make an estimation over the first 3 terms. And here we have 1, and here we have phi s normalized with respect to summer voltage. So for example, if we have 0.5 volt happen to be for our surface potential, then this is converted into roughly 20. Are you with me? When normalized with respect to the summer voltage, because summer voltage can be roughly 25 millivolt, so 0.5 volt can be regarded as 20. So compared with this -1, well, 20 and 1, should we have to consider this or not? Well, I think that still this is quite non-negligible. But anyway, when we make a comparison between these 2 numbers, the more dominant one will be this guy. And how about this one? Oh, we don't have to consider this first term because it has negative sign in its exponent, in its argument. So for positive surface potential, then it rapidly approaches to number 0. If we have positive one, so that makes sense. However, since this one has a negative sign in its argument, so we can safely neglect this guy. So now you understand why I have introduced only two terms highlighted in this case. Here you can see that when we have moderate value of surface potential phi s, not quite close to number like 1.0, 0.9, something like that, then usually this term dominate. And only when we have sufficiently high bending, then now this term becomes the dominant term. So please understand these two dominant terms. So it means that in this MOS system, we have two different mechanisms. The first one is linearly dependent on, at least in its squared sense, in its square rooted sense, the quantity is dependent on linearly on surface potential. And this guy exponentially dependent, but starting point is far behind this number. I mean that, well, if we write down surface potential and just to write down this linear term and exponential term, so let's just do it. Here we have 0, but we will not consider exactly 0 value, and let's say that this is our thermal voltage kBT over Q, and I will take just log 10 of this quantity. If I just take a logarithmic, semi-logarithmic scale of these two terms, then we will have just a simple, almost slow, quite slow behavior of our surface potential related term. N is divided by kBT over Q, and second term is starting from far behind it. However, since it is exponential, so when we draw it in its semi-logarithmic scale, then we will find that it has exponential increase, and eventually this linear term will be matched to the exponential term, and beyond this point, now the dominant term becomes the exponent one. So simply speaking, we have two different mechanisms, 1 and 2. But up to now, we have just solve Poisson equation and integrate something. For a while, we just forget about the physical meaning of this job. But now it's time to think about why we have two different terms in our resultant equation. Why do we have this linear term? And why do we have this exponential term? You should be able to name them. The linear term is corresponding to the depletion of your p-type substrate. Holes are depleted, so their dependency is really linear in terms of a square rooted way. And how about the second term, exponential dependence? And that exponential dependence is corresponding to the contribution from electrons, inversion electrons. So although for relatively low surface potential, we have a negligible electron density, but at least their dependency is really exponential. So although not clearly visible in this case because masked by our depletion charge, but there is exponentially growing term with respect to the electron density, and eventually at a certain point, now it will overwhelmingly important in overall charge contribution. So two different mechanisms to generate negative charges are reflected in these equations. Okay, do you have any question? I think that this is, of course, so let me just advertise our entire semester. Our entire semester, up to now we have thought about MOS system, but in my opinion, the most important one for MOS part, capacitor part, is this relation. Once you understand this relation, the next job is just understanding, interpreting. Yes, you can do it. After that, we will move to the long channel MOSFET. Long channel MOSFET is the simplest one we can imagine in our transistor. So that will be the second part, and eventually we will go to more advanced topic for state-of-the-art devices. But you know, this is the very first part of our MS capacitor, and this one is the most important one. Please try to understand the physical meaning of each term, and also you should be able to derive this equation from scratch. So sometimes maybe you are sent to a small island without any computer, any book, just a pencil and a sheet of paper. Even that case, you should be able this expression by yourself. Okay. Okay. So now hopefully yes.
그 리딩 코에피션트가 각각 1이랑 스퀘어
NI squared over and
그러니까 저 파이 S의 선형적인 게 지금 계수 1인 거고 그리고 저 exponential term은 저 P substrate의 그 농도라고 해야 되나? 홀의 농도?
yes, you're right. This is corresponding to the whole density and squared whole density, and therefore it is corresponding to square of Ni over Na. And you know, usually this number is quite small, like 10 to the minus 6 or 10 to the minus 7, 10 to the minus 8. So that's the reason why we have quite a small number in this exponential term. And this exponential term is corresponding to the electron contribution.
그 일렉트론에 관련된 텀이랑 묶여 있기 때문에 그래프가 저런 식으로
Yes. So for example, here, good question. So let me just do more clear math. Here, let's say phi s equal to summer voltage exactly. Then, in its normalized sense, Q, then it will become just 1, number 1. Then, when you have a look at this term, its value will be just Ni squared over Ni squared and number 1, and that becomes just a natural number E. Yes, and when we have a look at this term becomes just number 1. So this number is actually taking the log 10, then of course we will have a number 0, but for while just to write down its original value, then we will have a number 1. And here we will have a number like 10 to the minus 12, 14, 16, all kinds of these small number will occur at this point, because you know here we have this coefficient. So huge difference in its yes, so this is a logarithmic scale log 10. I will take the log 10.
exponential이니까
Okay, but oh yeah, yes, this straight line in this semi-logarithmic scale is corresponding to the logarithmic increase.
저 선형적인 게 지금 exponential
Yeah, sure. So this red colored one is corresponding to this one, and this relatively slow, almost constant one is corresponding to this guy.
교수님 보통 어떤 때 저 교차점이 생기나요?
Actually, that is the most important question, because in engineering sense, we wanted to find out that point. Okay, up to this point, we have not sufficient number of electrons. But beyond that point, we have sufficient number of electrons. That quantity is actually, maybe you have heard about this number, condition, threshold. So when you have threshold voltage and below threshold voltage, by the way, threshold voltage is a property of your gate voltage. So right now we are talking about surface potential. Surface potential and gate voltage are different quantities, and we have to also find out the conversion from gate voltage into the surface potential. Then how can you do that? So by solving the MOS equation, then we can do it. So anyway, so what is the boundary between these 2 points? So as I told you before, actually not exactly this point. There is some point where we have a difference between this mechanism 1 dominant and mechanism 2 dominant, and more or less their cross point are corresponding to the threshold voltage, but not exactly, because definition of threshold voltage, there are many different ones, and today we will talk about one of them. Okay, good question. And I wanted to stress this homework. So of course homework answer is given to our here. This is the answer of our homework problem, but the reason why I'm asking you this homework or assign this homework is, since this expression is so important, so please try to your own drawing. I have a lead and I understood. It doesn't work at all. So please do your drawing, do your calculation. This is really important. And yes, anyway, the homework is given as this way. Now you have the relation between QS and phi s. Where can we find it? Yes, equation 2.182. Just to draw it. I'm not asking you much intelligence, just to draw it, of course, at 300 Kelvin. Using some reasonable numbers, so now you can do it. That is the first part. And the answer is given here. If you draw it, then what you will get actually is this one. What you will get is this should be your answer in semi-logarithmic scale. Well, why do we have this deep? This deep occurs because at flat band condition we have a net zero charge. So this graph is drawn in semi-logarithmic case. So that's the reason why when you take the log function of a quite a small number, then you will have a dip. And in terms of our QS value, this is positive QS, and this is negative QS. So, you know, as I told you, if we apply high gate bias and we collect negative charge in our the opposite part, semiconductor part, so we have a negative sign. Then how can we get these graphs, this yellow colored one? Please take the absolute of your QS. Then you will have this kind of behavior. Okay. In this answer, you can find the additional lines like blue one or green ones. Those are not directly available from our discussion. So for a while, just to forget about them. Just to try to draw this yellow curve corresponding to the total amount of charge collected in the substrate. That was the first answer or first question of our homework. So please just draw equation 2.182. Then the next step is now you know ES, and ES, what was ES? This is the electric field at x equal to 0 interface, but at silicon side. So in order to convert it to the oxide side, we have to consider the ratio between permittivity values, and happened to be the number was just 3. So just to multiply number 3, then you will have oxide field. And when you have oxide field, by multiplying the thickness of this oxide layer, T-ox, then you will get the voltage applied to your oxide layer. So now please try to this job. Now you have given phi s value. From this given phi s value, you can calculate ES, obviously, and please convert it to oxide field, and from this oxide field, please calculate oxide potential difference. Then by summing them all, these two numbers, then you will find the gate voltage difference from flat band voltage. Then please calculate VG as this form. Of course, this Vox is a function of once again surface potential, and now you have a flat band voltage. Wow, it means that starting from a given phi s value, you can always find out the corresponding gate voltage. So now please try to calculate this one. Now draw your QS not as a function of a surface potential, but a function of gate voltage. How can you do that? Once you make the table between phi s and Vg, then since you know always Qs, just neglect this Q phi s and draw their relation. Of course, there is no guarantee that these numbers are uniformly distributed. Maybe you can have a uniformly distributed phi s, but your Qs and corresponding Vg can be sometimes densely populated and sometimes loosely populated. Doesn't matter. You have a sufficient amount of computing power just to draw it using your Excel, MATLAB, Python, whatever. So you can draw it. You will have a very beautiful graph, and that is the point. So by this way, solving this way, you will find this form. Oh, Qs, of course, its absolute value can be written as a function of Vg, and you will find a certain quite interesting behavior. Please do that job. That is my homework. And once you can do this homework, I think that you understand the essential part of this modeling. I think that nothing further. The essential part of this MOS analysis is this one. You have a MOS equation. MOS equation is really global. It was just a division of a potential into oxide part and semiconductor part. Oxide part, that was easy. However, semiconductor part, that was difficult. But in the case of a planar MOSFET, fortunately, we can find out this expression. So for planar MOSFET, we can do such kind of a calculation, and by solving that MOS equation together with the relation equation 2.182, then you can solve the system and also find out information. So now you understand. When I apply, for example, 1 volt, I will have a total amount of charge, something like that. So you will get that one. So please try to draw it. Okay. Any question about homework? So by the way, you don't have to submit it, but since this is really important to understand the lecture content, please, I strongly recommend you to all of you do your homework. Okay, so now if you successfully draw equation 2.182, then you will draw this yellow line. When you take a Q, absolute value of QS, you will find this one. And if we can further decompose that into contribution from electrons and holes, then now we can decompose these two numbers. So here we have one and the other, and this green line is corresponding to purely electron. So this is corresponding to electron density integrated over from 0 to infinity. This is drawn. And second part, this blue one, is the other. What is it? This is corresponding to the hole density, but hole density is negative, also positive, and Na. Na is positive. You know, hole density is positively, holes are positively charged, and these acceptors are negatively ionized, and we are just drawing the integration of P and P minus Na. It is corresponding to this blue one. So now what we can expect is, for example, if our gate voltage, this is not sorry about that, this is not surface potential, but it is drawn as a function of a gate voltage. And if we have a gate voltage below this point, then, well, almost there is no contribution from electron density. Question is it really 0 or not? No, it's not 0. But where can you find it? Because we are just limiting our lower y limit 10 to the 10. That's the reason why we don't have any contribution. Even for this case, we have extremely small values for our electron contribution. But this is really negligible. And beyond that point, positive certain gate voltage, then now we can have sufficient amount of considerable amount of whole contribution. And at this point now we have really same amount of contribution from electrons and holes, and beyond that it becomes dominant factor. And interesting point is, although we have, please note that here, roughly speaking, this is corresponding to about 0.7 volt, and here we have 2 volt, and difference is 1.3 volt. Although we have applied additional 1.3 volt to our gate metal, please try to estimate the change of charge due to holes. How large is it? So can you identify any difference in this number? So can you find any, how large is it? So it is very difficult to identify the difference. So it means that beyond that point, actually depletion charge contribution is almost constant, and depletion of holes becomes quite ineffective. Then naturally we can ask this question. Previously here, this part, the major mechanism to obtain negative charge, further negative charge, was actually depletion of holes. But why it becomes ineffective so much? Please think about this one. This is not a sole performance of our hole depletion. They are competing. I mean that they means that two different mechanisms. We wanted to have a negative charge, and there are two guys. One is inversion electron, and one is hole depletion. And if inversion mechanism becomes quite ineffective, then this hole depletion can perform some roles. However, now at this bias point, high gate bias point, now electron inversion becomes too effective. So there is no room for our depletion charge or depletion mechanism to play. So that's the reason why it is almost flattened here, and almost all kinds of contribution comes from these electrons. Of course, we can continue this discussion in next Monday, but I hope that already you have distributed lecture material, so please preview this lecture material and we will just follow the lecture material. Okay, so if you have a further question, please come to me after this session is over.